Okay, everyone. Online students, do you hear my voice?
Yes, Professor.
Yes, Professor.
Okay, fine. But you're also fine. Okay, now let me just show you where you find the links to the recorded video. Okay, so when you go to Google Classroom, there is this stream section. Okay. There are several posts. Okay. One of them is specifically about the recording. Okay. So in this thread, there are many comments. Okay. And in the comments, there are links. Links to the class video. Okay. So you need to look into the comments to find the links. Right. So last week, this is the Wednesday section. This is Thursday. And then previous week, this is Thursday. And then this is Wednesday. So I'll keep posting it here in the form of comments. Okay. Okay. Then. Okay, so last week we stopped here. We talked about marginal effect. Introduced the concept of marginal effect. Okay. So in a plain linear regression model, the slope coefficient.
Your voice is very unclear. Professor, your voice is very unclear.
How about this? Is it the same? Same. I just switched mode. See what happens. How about this one? Your voice is not coming from the mic you are using. How about this one? Same. I don't know if it works. Does it work? How about this one? Same. Same. What's happened? How about this? Better? Didn't make any change. Still same.
Still not clear.
Still not clear. I'm not sure. So it sounds like the voice is coming from Carmen. Or in the wrong channel.
Yes.
Uh, 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 uh,
Yeah, it's this one.
How about this one? How about this one? Still the same?
It's echo.
There's a lot of ego.
Yes.
I'm aware. But does it sound closely enough?
Where is it?
Uh, uh, not sure. Yes, there is.
พี่แซมครับเสียงมันเอ็กโคจากไหนผมลองเปลี่ยนแล้วครับพี่แซมแต่ว่าไอ้ไมโครโฟนคือมันเป็นทั้งสองอันเลยพี่ทั้ง Echo Cancelling แล้วก็ไมโครโฟน
From here. How about hello? How about this?
Test, testing. Guys, in the Zoom call. Oh, there's still the echo. Right?
Yet we can hear.
You can hear us, right?
Yes, yes.
Very clear, no echo.
Yeah, not at the moment.
It's like the there's like I don't know which one, but like even like the smallest volume from like your computer can like disrupt the microphone. Even your computer. You all muted your speakers, right? Not the microphone, the speakers. Can you all just make sure you all mute your speakers? Not the microphone, just the speakers. Ah. Testing. Okay.
Yeah.
I wonder. This one's never muted, right?
This one?
Yeah, this one. You can mute that one. I can mute, right? Can you hear me?
Yes. Yes.
No echo anymore, right? None at all?
Yeah, none at all.
I think it's fine now.
That's right. Okay. Thank you, Ben. That's good. Okay, thank you very much. I'm not sure. Okay, students, do you hear my voice closely?
Yeah.
Sounds like usual.
Yes.
Okay.
Finally.
Okay, then let's start the class. Okay, thank you, Bank and Agnes. Maybe because we used it last night. For...
This morning, Dr. Vilas used it.
Oh, he used it?
Nothing.
Okay. Okay. So last week, we discussed a simple regression. Okay. And then with that, I explained how to quantitatively interpret the slope coefficient. Okay. So we will extend it to the multiple regression. Multiple regression means having more than one x. Okay? Which is what you're supposed to do in the actual research thesis, dissertation. Okay. Okay, so now the difference is we have x1, x2, x3, as opposed to just x1. Okay, but the rest is the same. Okay. Okay, so the purpose is very low. Very low means very small. Eva,
Yes, it's very low. Sound is very low.
Where is the other one? Okay. Okay, so let's try this one. How about this one?
Yes, it's very good.
It's better.
Yes.
Yeah.
Yes. Okay, this one.
It's good.
You hear well?
Yes, it's good.
It's good?
This one is good.
Okay. Yeah. So as before, when you have more than x variables, the basic procedure is the same. We try to minimize the squared errors. Okay? So simply put, we try to minimize epsilon. Okay? So we will find the combination of b values, b0, b1, b2, b3, so that epsilon will be minimized. Okay? Epsilon is the difference between the line and the actual data. Okay? So that way we will find the set of b values. Okay? The set of b values means one intercept and 3 slope coefficients. And you are interested in finding the slope coefficients, basically. Okay? Okay. So procedure-wise, it's the same. Minimization of least squares. Minimization of squared errors. Okay, so this method is still least squares. Least squares. Okay. And then, yeah, as we assume this error is random, then we call it ordinary. Ordinary least squares. In short, OLS. Okay, in short, OLS. So this is what we call this model, basically. Okay, so when I say OLS, it means multiple linear regression. Okay, the simplest model, which has a lot of limitations. So we will also explain improved models. Okay, but this is the starting point, OLS. Okay, so in this example, we have, in addition to years of schooling, now we have age and land size. Okay, age and land size. Okay, so let's analyze this OLS in R. Okay, so please open your R. Okay, so the code is already in the script file, so you don't have to write it. Okay, but yeah, if I just explain what the code means. Yeah, it's the same as the simple model. The only difference is now we have more than one x variables. Okay. When we have more than one, then we use this plus sign, and then put more variables. Okay, this plus is not a summation. We just indicate we have more variables on the x side. Okay. Otherwise, it's the same, completely the same as before. Okay. So I just gave this name, multreg, to mean multiple regression. Okay, but this name is arbitrary. It can be anything. Okay, so please do it in R. Yeah, let's share R. Oh. Okay, now you see R, right? Okay, please open your script file. That's the first thing to do. So now you are using 5.11. 5.11. Okay, so this is your script file. Okay, the next thing to do is to read the data and attach the data. Okay, so you execute the first line, Control R or Command Enter. Okay, Control R, then the File Explorer opens. So you select the CSV file, open. Okay, and then after selecting, you attach. Okay, attach data, Control R or Command Enter. Okay, so now you are ready. Now you're ready. So you go down and find multiple regression, this one. Okay, so this one we do. So this is what we just saw in the PowerPoint. Okay. So this is the dependent variable. Okay, left-hand side variable. And then, so this entire thing. Okay, this is the y. And then x1 is this one, followed by plus, and then the second x, and then again plus, and then the third x. Okay. Okay, so please execute these two lines to show the result. Execute. How is it? Does it look the same? You got the regression results? Okay, so now you have one intercept and three slope coefficients. Okay, so just next to the variable names, the first column, it says estimate. That is the coefficients. Estimated coefficients. Calculated B coefficients, B0, B1, B2, B3. Okay, so that is the so those are under the header estimate. Okay? Yeah, and then the next thing to worry about is P value. So that is in the far right column. Okay, it says PR. So that means P, probability. So which slope variable, which slope coefficients are significant? Yeah, first of all, education. Significant? Age? For age, p-value is 0.40. It's large. Okay. How about land size? Land size is also significant. P is small. Okay. So that's what you can find here. Okay, so in the updated version of the R script file, I added one line here. You may have noticed. This is related, I think Sisa asked a question last week or several days ago. So how to show the sample size? In the regression result, the sample size is not shown. Okay, everything else is there. F statistic, squared, all the coefficients, p-values. Okay, but the sample size is not there, which you are supposed to show when you present the result. So this one line can do it. NOBS, number of observations. Okay, included in this analysis, multreg. So you can execute that one. Then simply it shows one number, 246. So that is the sample size included in this analysis. Okay. Okay, then go back to PowerPoint. Okay. Where is that? Okay, so this one, you already executed it. Okay, so based on that result, you are supposed to show this kind of table. Okay, you have to present a good-looking table. Okay, showing coefficients and the p-value. Okay, and then using asterisks, remember? It is customary to put some asterisks, the stars, on the coefficients or p-values. So I just put them on the coefficients. I think I'm more used to doing this. Okay, so on education, because p-value is smaller than 1%, I put 3 asterisks. Okay. Okay, coefficient of age. I don't put anything. Okay, so this indicates the coefficient is not significant. Land size, I put 2 because the p-value is below 5%. Okay, not below 1%, but still below 5%. So I give 2. Okay, 2 stars. Okay, constant. This is intercept. B0 coefficient. This one was not significant. Okay, so you don't put star. Okay, so this is how you present the results table. So of course you have to show what the dependent variable is, and also the unit. Okay, unit is essential. You have to show it. Otherwise, you cannot quantitatively interpret the coefficients. Okay, and then sample size is there, and then other things for formality. Okay, a squared F statistic, that kind of thing. Okay, but the main results, key results are the coefficients and the significance. Okay, of these 3 variables. Okay, so let's interpret these quantitatively again. Okay, so we focus on the slope coefficient. So we don't bother with constant. Okay, so this, 3 coefficients. So how are we going to interpret? B naught was insignificant. B sub 1, it was highly significant. And the coefficient was 3.044. Okay, so you interpret it this way. When education increases by 1 year, non-agricultural income increases by 3,044 pesos on average, holding other variables constant. Okay, so now you have this one. Okay, in one independent variable case, we didn't have it because we didn't control for any other variables. So now we have it. Okay, so we are controlling for all the other variables included, namely x2 and x3. Okay, age and land size. So when you compare, when you find the effect of education, other factors like age, land holding, those things are kept apple to apple. Okay? We did a fair comparison in terms of these two variables. So we are not affected by these two. Okay? Okay. Yeah, so some terminologies. We sometimes say covariates to mean other variables, which are likely correlated. So there are some nuance carried by this term, covariate. Okay, variates together, so it changes together. So we assume there's some correlation. Okay. So holding covariates constant. Okay, so that's what this analysis does. Okay, age coefficient insignificant. Okay, so either we don't say anything, or if we were forced to say something, then we can say something like, on average, age has no significant effect on non-agricultural income, holding other variables constant. Okay, so on average, no effect. Maybe individually, some people have positive effect. Some people have negative effect. But as a group, okay, when you take the average, then no effect. Okay, B3. B3 is the coefficient of land size. Okay, so now it's 5,141. When field plot size increases by 1 hectare. So when you look at the data file, the original data file, you can see the units of all the variables. So this field plot size variable is measured in hectare. Okay. Yeah, so 1 hectare is like 2.5 acres, and also about 6 rai in per unit. Okay, but hectare is the most international land size unit. Okay, so here we use hectare. Okay, so when field plot size increases by 1 hectare, then non-ag income increases by 5,141 pesos on average, holding other variables constant. So this is the full form of quantitative interpretation. Okay. So do you get the meaning when you read this? Okay, so for education, when years of schooling increases by 1 year, so it doesn't matter from which year. Okay, it can be from 5 years of schooling to 6 years of schooling. It can be from 9 years of schooling to 10 years of schooling. Wherever you are, we are talking about an increase by 1 year. Okay, land size as well. Whether large holders or small holders, we are talking about just 1 hectare increase. And then what would happen to the dependent variable? Okay? Okay, so these coefficients, these are the marginal change in the dependent variable. Okay? So that's why it comes with the unit of this dependent variable, pesos, currency. Okay, so that's why we talk about pesos, pesos, pesos everywhere. Okay, so from this you can say education and land holding have positive and significant effects on non-agricultural income. Okay, so significant means statistically significant. P-value being small. That is the meaning of significant. Okay? Positive means the coefficient is positive, not negative. So when land holding size or education increases, then non-ag income also increases. Sometimes it can decrease depending on what the variable is. If the coefficient is negative, then you interpret it negatively. Okay? If this variable increases by 1 unit, then the non-agricultural income will decrease by this much. So if the coefficient is negative, you will interpret it that way. Any question about this? Yeah, this is one of the very important points. Okay, so when you write a research report, you have to explain, right? You have to explain your results. Okay. Yeah, there are some words you can use. Okay. One example is effects. Okay, effects of variable A on variable B. So A is basically X, and B is basically Y. So effects of something on something. That is one type of expression you can use. Also impacts. Sometimes you can replace this effect with impact and say impacts of something on something. Okay. Yeah, so please be strict about the use of prepositions. Okay, of, on. Yeah, don't say instead of on, to. Some students use to, but don't use it. It's not common in research articles. Okay, so impacts of A on B, or you can also say influences. Influences of A on B. Yeah, very similar expressions. Now, in terms of verb, okay, you can also use a verb form. Affect, okay? A affects B. Or A impacts B. Or A influences B. A causes B. Or A determines B. Or A drives B. So these verbs you can use almost interchangeably, but not always. There are slight nuances. Okay. Yeah. Okay, so now multiple regression has the ability to estimate the effects, okay? As long as you have multiple X variables. Okay, so it has the ability to estimate the effects or impacts of X on Y, okay? Which is different from just correlation analysis. From correlation analysis, you cannot say much about the causality or effects. Okay? So this is why we can use regression analysis to prove or disprove your hypothesis. Okay? You have some hypothesis you establish in your chapter 1 when you write a thesis. Okay? Then through this kind of analysis, you can prove or disprove your specific hypothesis. Okay? And that result can be used to inform policy designs or policy making and make some implications. Because now you are talking about the causal effect, not just correlation, accidental correlation. Okay? Okay, so after describing the quantitative interpretation, you will write some implications. Okay, that's what you normally do. Okay, after showing the table, first you provide the direct interpretation, either quantitative or qualitative, some direct interpretation, and then you discuss what that result means, what that effect means in terms of development, okay, or policy formulations. So there you can use these kind of terms. Okay, you can say that the result suggests that blah 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 blah. Okay, if you increase education, then the poverty will decrease. That kind of thing. Result shows, result indicates, implies. Going down, the expression is stronger. Okay, so implies is the strongest among these four. Suggest is the weakest. Okay, so you pick the right word based on how confident your result is. Okay, if the analysis is really good, if the data are very good, and you're confident in your result, then you can use strong expressions. Okay, but strong expressions are also risky. It can attract criticism or rejection. Okay, you may receive tough comments if you always use strong expressions without showing good evidence. Okay, just talking too much. Okay, this implies, using this expression without showing enough evidence, then you will be criticized. So that is also risky. Okay, so safe driving is also important. When the result may not be so strong, okay, you are supposed to use a weaker expression. Okay. Okay. Any question about this? Interpretation and implication.
Professor,
Yes.
could you explain why it's called covariate variables, the other variables?
Other variables.
Yeah, in the previous slides you've mentioned they're called the covariate variables, right? Yeah. Yeah. Like, yeah, what does covariate variables mean here?
The meaning.
Yeah. Yes.
Meaning is the variables, other variables included in the same analysis, the same model, the same equation. Okay, so when you are concerned with effect of education, then the covariates are the other variables. Okay, so age and the land holding. So those variables are supposed to change together. They're supposed to vary together with the variable of interest. However, in this analysis, you are controlling for them. You are fixing them, okay, not to move, while you are estimating the effect of this. Okay? So covariate, this implies these variables move together with x1. Okay, but you are controlling for them so that they will not move. Okay, so if you don't control, they will move together. So that is what is implied by this name, covariates.
Okay.
Okay, so that is actually related to what I'm going to discuss in this green sentences. Okay, multiple regressions can control for covariates. And this feature is particularly important. Okay, because that way you're more likely to be able to explain the effects, causal effects, rather than just correlation, which doesn't support causal effects. Okay, so this feature is important, and it has, you can use this terminology, ceteris paribus. This is a Latin term to mean this concept, holding other variables constant, or other things being equal. This is the original meaning. Other things being equal, all other things being equal, other things held constant, or all else unchanged. Yeah, similar expressions meaning the same thing. Okay, so this means you're controlling for all other factors included in the model. Okay, so if you don't include, you cannot control. Okay. Yeah, so sometimes you can just say ceteris paribus instead of saying holding other variables constant. You can also say it. For example, here, when field plot size increases by 1 hectare, then blah, blah, blah income increases by 5,000 on average, ceteris paribus. You can also speak like that. Okay? It's the same meaning as this one, holding other variables constant. Okay, yeah, so please make sure you understand this concept of ceteris paribus. Okay, controlling for covariates. Okay, so the next one is dummy variable. So I think we take a break before that. Okay, so let's take a 10-minute break. You still hear me?
Sorry, sir.
Oh. Oh. Okay. Everyone ready? Okay. So now we start talking about some modifications or some useful techniques within OLS, within multiple linear regression. Okay, actually within multiple linear regression, you can do so many things. Okay, this is one of them, dummy variable. Okay, sometimes you want to consider an explanatory variable that is not a continuous variable. Or let's say that is not a numerical variable. Okay, not only continuous, but discrete variables like age, that can be included. It was already there, right? But sometimes not even discrete. You want to examine a categorical variable. Okay. So one very important example of a categorical variable is when there are only two categories. When there are only two categories, then usually we express it in terms of 0 and 1, like a coding. Okay. Okay, so it's not a numerical number. It's not a quantity, it's just a code, 1, 0. Okay. For example, gender. You want to include gender as one of the explanatory variables, as one of the X variables, okay? To see how gender affects some outcome, some result, okay? So in this case, non-agricultural income. Okay. So we can also say a binary variable. Okay, when there are only two categories expressed as 0 or 1. You can also say binary. Okay, so binary variable is a special case of a categorical variable. Okay, when there are only two categories. Okay, so gender we usually consider only two cases, man or woman. Okay, in this data set that you are using, it is coded this way. Code 1 is given to two men, and code 0 is given to women. Okay, so when you look at the data set, there is a variable, there's a column, a gender, in which you find the numbers coded 1 or 0. Okay, so you see only 1 or 0 when you look down through different households, okay, different respondents. Okay, so there are 246 observations, okay, each of them having either 1 or 0. Okay, so that is how the variable is. Okay, but this can be vice versa. It's okay to assign 1 to women. That is also fine. Okay, that is arbitrary. Okay. Okay, now, yeah, so this kind of variable, binary variable, it can be used for any two category cases. Yeah, let's think of some examples. The result of coin toss. When you toss a coin, and then Sometimes you see the head, sometimes you see the tail. So you can code 1 for head, 0 for tail, or vice versa. Okay, so there are only 2 outputs, 2 cases. Or answer to a closed-ended question. So in the questionnaires, you ask some closed questions, which is answered by yes or no. Okay, so the respondents gave the response in the form of yes or no. Okay, so that can also be coded 1 or 0. Usually we put 1 for yes, but it can be the opposite. Okay, so depending on the respondent's answer, in the data set, you store the information in this form, 1, 0, 1, 0, 1, 0. So 1 means yes, 0 means no. So some respondents answer yes, others say no. For a specific question you asked. Okay. So that is also one example of a binary variable. Other examples, something successful or not. Yeah. For example, whether the respondents received some training. Okay, you ask the respondents, did you receive this training in the past 12 months? Yes or no? So that kind of thing. Or, yeah, did you successfully adopt a particular technology introduced to this community? Already adopted? Yes. If not yet, then no. So that kind of information is also binary. Okay? Or on, off. Okay? Or good, bad. Or treated, controlled. Okay? Treated means receiving some treatment or project, some intervention, or in some cases, some capacity building intervention. Controlled means receiving nothing for comparison purpose. This is also important. When you want to conduct an impact analysis, impact assessment, you have to have this variable, treated or not. Okay? So some people are treated. Okay, so you code them 1. Some people didn't receive training, then you code them 0. Okay, then analyze that variable. How the training receipt status affects some output. Okay, that is very often research interest. Okay, so all this, anything that comes in a binary response form. Okay, anything that has only 2 choices of output. We can call them a binary variable. And then we code those variables in terms of 1 or 0. Okay, now we are talking about analyzing a binary variable as one of the x. Okay, you can also analyze it on the left-hand side as a dependent variable, which we will discuss later. Maybe in November. Okay, but here we are talking about the right-hand side, x variables. Okay. Yeah, in this case, we often call it a dummy variable. Okay, so dummy variable is basically a binary variable included in regression analysis. Often as an x variable, but not always. Okay, so let's see how we analyze a dummy variable. So now we have gender dummy. Yeah, we can say dummy variable, or sometimes we just say dummy. Okay, so gender dummy we have. So in this case, 1 indicates men, 0 indicates women. Okay, we already have that variable. ready for analysis. Okay. So in the analysis, we just add binary variable as one of the x. Okay, you don't have to do anything else. Okay, and then show the result. Okay, can you do it in R? So let's change. Okay, so now you have R, right? So below multiple regression, we have this one with a dummy variable. So you include one dummy variable on the right-hand side. Okay, as you have just seen in the slide. Okay, so this is the only change we make compared to the last one. Okay, and then I just give this arbitrary name. Because a dummy is included, I just say dum reg. Okay, so let's choose these 3 lines and then execute the analysis. Do you see this result? Same? Same, right? Huh? You have the same result?
For the last line, I don't have last line. I have just only the second line, 2 lines, but for you is a 3 line.
Yeah, actually there's a new version. So, but that is just to show the sample size. It's not so different. Okay, but you need to include. You need to make sure you have gender now. So this is just multiple regression. Now we are here. Okay. We are analyzing a dummy variable. Okay. Yeah, so one section below multiple regression. This is also multiple regression, but with a dummy variable. Okay. So make sure your result includes gender. If not, there's something wrong. Okay. You found it? Yin? Okay. Did you try?
I have some case same because I don't have this line in the R script. I don't have.
Yeah, if you download it again, you have it.
Download.
But it's not a big deal. It only shows the sample size 246. Yeah, this is okay.
Professor,
Okay. Yes.
I don't have the last line.
Last line, yeah, that is in the updated version. It's in the Google Drive.
Okay.
Okay. Yeah. But it's not a big deal. That is just to show the sample size. That's not the main result. Okay, so you can still see the main results, including gender. Okay. Yeah, you can either download the new version or you just type because it's very simple. Okay. And obs dum reg. So typing is not so cumbersome. Okay. So you get the results. Okay, so you check the coefficients and p-values. So coefficients, education is about 3,000. Gender about 12,000. Okay, age, field, area. Not so different from before. Okay, and then you check the p-value. Still, education and land size are significant. Okay, now the key variable you added, gender. This one also has small p-value. Okay. So the coefficient on gender is about 12,000 and statistically significant. Okay. So that is the finding. That is the finding. So now you go back to PowerPoint. Okay, so how are you supposed to show it and then interpret it? Okay, so this is the result you obtain. So the new thing is this one. Okay, now you have the gender variable. Okay, that came with this coefficient, with this significant p-value. Because the p-value is below 5%, I give 2 stars. Okay. Okay, what does it mean? How will you interpret it? Yeah, first of all, remember how it was coded. 1 for men and 0 for women. Okay. So when you put the gender variable, usually you explicitly show which one is 1. Otherwise, people get confused. Because there's no common rule. Okay, some people use 1 for men, others use 1 for women. It's quite mixed. Okay, so you need to show it. You need to show the definition, your definition. Okay, and then the coefficient is positive. Okay, what does it mean? When coding is this way, okay, 0 for women, 1 for men, and then the coefficient was positive, that means the outcome is higher for men. Okay, in this case, income, non-agricultural income is higher for men. That is the basic qualitative interpretation to begin with. Okay. So now, quantitatively, how will you interpret it? One way you can interpret it is, if a woman became a man, holding all other factors constant, her non-agricultural income would increase by 1,2,384 pesos on average. Okay. So we are not necessarily looking at the difference between men and women. We are talking about changing the gender, changing the sex, because all other things are held constant. Okay? If you are comparing different people, okay, comparing men and women, then all other things are also different. Okay, men and women have different education level, different age, different land holding size. Okay? That's not what we are doing. We are not comparing these women and these men. We are comparing, not comparing, we are looking at the effect of gender. We focus on the effect of gender, and other variables are controlled for. Okay? So we are talking about marginal change. One marginal change for a binary variable is, it means changing from 0 to 1. Okay? So the situation we are considering here is, if we change this variable from 0 to 1,
Okay, that is what we are looking at. Okay, just like this one. Okay, remember education when you interpret education effects. If education years of schooling increases by 1 year, that is what you are talking about. Now for gender, because there are only two choices, our interpretation goes like, if this gender variable changes from 0 to 1. Okay, because it cannot change from 1 to 2, because there's no 2. Okay, so we only talk about change from 0 to 1. So that means change from women to men. So if the gender switches, only gender, other things held constant. Okay, of course there's gender gap in education, there's gender gap in landholding, but those factors we control. Okay, and then look only at gender. Okay, so that is why we use this kind of expression. If a woman became a man, then this would be the average increase in non-ag income. Okay? But you don't always have to say this. Okay? Woman becoming man. Sometimes it's a bit weird. Okay? You can also say more simply like this. The average gender effect on non-agricultural income is 1, 2, 3, 8, 4. That is also possible. Gender effect is this much. Okay? But you have to be on the same understanding that we are talking about men having higher. Okay? Not women having higher. Okay, so you have to make it clear how this gender variable is defined, coded. Okay, so as long as it's clear, then you can just say gender effect is this much, simply. Okay. Or another possibility is this one. The average effect of being a man on non-agricultural income is this one. Effect of being a man. Okay, so implicitly, you are comparing with women. Okay. Any question about this? Now I will show a graphical representation of this interpretation. Okay, so the results were like this. Intercept, okay, B0, and slope on age, those were insignificant. So you don't interpret, or you don't consider them as non-zero. Okay, basically we regard them as kind of zero. Okay, but all other slopes, B1, B2, B4, these were significantly identified. Okay, and these were the numbers, coefficients. Okay, because gender is binary, there are only two cases, we cannot put it in the x-axis. Because the x-axis shows a continuous transition. Okay. So we cannot put gender in the y-axis. So instead, we put something else. Let's use education, years of schooling. Okay. So now we put a covariate education on the x-axis. And then see how we can understand the gender effect. This B2. Okay. So now B1, yes, X1 and B1 are also in the picture. But the purpose is to understand the B2. Okay. First of all, effect of education was 3,000, right? 3,034. So that was the slope coefficient. Okay. So if education increases by 1 year, then non-agricultural income increases by this much. So that is a slope coefficient. Okay, so it will be like this. It's an upward slope, straight line, to show the relation between education and income. Okay, and then the slope, this one. Okay, both lines, one for women, the other for men. Both lines have the same slope. Okay, 3034 in this specification. Okay, so if you increase education, by 1 year, then on average, the increase in non-agricultural income is 3,034. Okay, so this is 3,034. If this increase is 1 year. Okay, so wherever you increase 1 year, whether you do it here or here or here, same slope. Because the relation is linear. Okay? Yeah, so this slope represents B1. Okay? Now, how is the dummy variable captured? This B2. Okay, so gender effect was 1, 2, 3, 8, 4. Okay, for women, your x2 is 0, right? For women. For men, your x2 is 1, okay? Because that's how you coded it. What does it imply? For women, this term is 0. For men, this term is 1, 2, 3, 8, 4. Okay, other things are the same. Okay, so in terms of the level of y, the difference between men and women is captured by this one. Okay, because only for men you have this. For women, because this is 0, then this coefficient doesn't make any sense. Okay, because this times 0 becomes 0. Okay, so for women, this term doesn't count. For men, this term counts by this much, 1, 2, 3, 8, 4. Okay, that is captured by this vertical distance. Vertical distance between the women's line and men's line. Okay, because of how the dummy variable was coded. Okay, for men it was 1. For women it was 0. Okay, so it's the vertical distance. It's not the shortest distance. Shortest distance is like this, right? It's not the shortest, it's the vertical distance. Because it's a measure of y. Okay, it's a measure of y. Okay, y is measured this way, vertically, not in the tilted way. Okay, so we are always talking about this vertical distance. Does it make sense? Okay, so this is how the coefficient on the dummy variable is represented in the graph. But the graph is two-dimensional. Okay, it's not three-dimensional, so there's a limitation. We can only consider one more continuous covariate. Okay, so we cannot include other things like land size, age. Any question about this? So this graph captures B1 and B2. Okay, B1 and B2. B1 in the form of the slope. B2 in the form of the vertical distance. Okay. Okay, what if it's not a gender dummy, but a training dummy? Let's say local people received some management training. Okay, if they received, then we code them 1. If some people did not receive, then we code those people 0. Okay, so we can consider training dummy. Training status, 1 or 0. Okay, so that kind of analysis is possible. Okay, if the coefficient was found to be 10,000. Okay, so that means this B2 was found to be 10,000. Then how will you interpret it? That means this distance is 10,000. Okay, and then this line is for those who didn't receive training. This line is for those who received training. Okay, so your interpretation goes like, receiving the management training would increase income by 10,000 on average, other factors being unchanged. So that kind of interpretation you're supposed to provide. Okay? So that means not for gender, not only for gender. You can consider various things. Any question about this? Okay, if you're okay, then we move to the next related topic. Yeah,
Professor,
You're
I
okay?
have a question. Is
Okay,
is it possible that the coefficient is negative?
yeah,
And
it's possible.
how can we understand it?
Sometimes it can be negative. For example, for some things, men can have a smaller value. Maybe if you're assessing the time spent at home, okay, then you will find a negative coefficient. Okay, so depending on what variable you're analyzing. If the y variable is time spent at home, okay, and then x2 is the gender dummy, where 1 is men, 0 is women. In most households, men spend less time at home, especially in rural areas. Okay, then in that case, probably you will find a negative coefficient. Because men tend to have fewer hours spent at home. Okay, so that is also possible. But another possibility is when the coding is the opposite. If you give 1, okay, if you code women as 1 and the men as 0, okay, in this analysis, okay, same this income analysis. Okay, then what would happen? women coded with 1, then you get the negative coefficient. Because women have lower income in this data. Okay, so yes, very possible. You can have negative coefficients, just like other coefficients. You can also have insignificant coefficient if the p-value is large. Okay, is it clear?
Yeah, thank you. But if the coefficient is negative, is the interpretation the same?
As a result, it will be the same. Okay, just a matter of how to put it. Okay, so men have higher income and women have lower income. They mean the same thing, right? So if you directly interpret it, then yeah, so in one case you will have men have more income by this much. In the other case, you have women have less income by this much. But the meaning is the same. As long as you're working on the same data. Okay, the resulting meaning will be always the same. It's just a matter of different ways of expressing the result. Okay. Now we continue using dummy variables, but for different purposes. Okay, we just analyzed a binary variable like gender. But sometimes you want to analyze a categorical variable that has more than 2 categories. Okay, maybe you want to analyze ethnicities, nationalities, that kind of thing, or which university you come from, or which district you are from. That kind of variable tends to have more than 2 categories. Okay, so one variable can have more than 2 possibilities. That can also be analyzed. Okay, the effect of a categorical variable on some output. That can be analyzed, but not as it is. You cannot just include a categorical variable into the model. If a categorical variable shows like Thai, Indian, Vietnamese, Japanese, Chinese, okay, you cannot just include it because those are text information. Software cannot understand. Okay, so you have to do something. Okay, so you can include a categorical variable as an explanatory variable into a regression model, but you have to convert it. Okay, how? You have to turn that categorical variable into dummy variables. Okay, dummy variables. More than one dummy variables. Okay, so you generate dummy variables from one categorical variable that you want to analyze. Okay, for example, yeah, the simplest case, just 3 cases. Municipality, this is the admin unit. Okay, so in the Philippines, you have province, of course, but then you have municipality. Below municipality, you have a barangay, smaller unit. Okay, so it's relatively large. Okay, but not as big as province. Maybe like a district in Thailand. Okay. in this data set you're using, people come from 3 municipalities, 3 neighboring municipalities, okay, not far, okay, from the same area basically, but 3 municipalities. Okay, so some people are from municipality 1, some are from municipality 2, the rest are from municipality 3. Okay, and then you want to examine whether this municipality influences the output variable. Okay, in this case, income. Okay, so to see whether there is any effect of municipality, location effect. Okay, but you cannot just include this one categorical variable into the model. You cannot do it. Okay, so you generate dummy variables. How? In the case of gender have 2 categories. Okay, and for 2 categories, we had 1 dummy, right? In our case, dummy for men. Okay, so 1 indicating men, 0 indicating women. So that means that dummy variable indicated men, basically. Okay, but implicitly, women were a reference category. Okay, so dummy for men means it is in reference to women. In reference to women. Okay, so that is why for 2 categories, we used only 1 dummy variable. We didn't use men dummy and women dummy. We don't have to. We just use 1. Okay, for 2 categories, we use 1. Okay, what about this one? Municipality. It has 3 categories, right? From which we create 2 dummy variables. For example, dummy for municipality 2 and another dummy for municipality 3. Then implicitly, municipality 1 is the reference category. Okay, for reference category, you don't do anything. Automatically, implicitly, that is the point of comparison. Okay. Now, how will you define the dummy variables? So the original variable is like this. Okay, municipality variable. Okay, so original variable in your data set looks like this. Municipality variable, which is categorical. So it shows municipality 1, municipality 2, municipality 1, 3, 3, 2, 1, blah, blah, blah. Like this. Okay, so it can be specific names. Okay, may not be number. Usually, when you collect data, it's easier if you use number, if you use coding like this, okay, instead of typing all the municipality names. So most likely, in your raw data, you will look this kind of coding, but it doesn't matter. It can be actual names. The point is, from this 1 categorical variable, having 3 categories, you generate 2 dummy variables. 2 dummy variables. Okay, 1 dummy for municipality 2, another dummy for municipality 3. Okay. Remember, a dummy variable is a binary variable. It's a 0-1 variable. Only 0-1. Okay. So municipality 2 dummy means it takes the value of 1 when the municipality is 2. Okay? It takes the value of 1 when the person comes from municipality 2. Okay? Otherwise, 0. Otherwise, 0. So if the municipality is municipality 1, then 0. Okay? If the person is from municipality 3, then it's 0. Okay? So for this variable, municipality 2 dummy, you give 1 only when the municipality is 2. Municipality number 2. Okay? Otherwise, 0. This one. If 1, if living in municipality 2. 0, otherwise. Okay, same thing for municipality 3. Municipality 3 will be 1 if living in municipality 3 and 0 otherwise. Okay, so municipality 3 dummy will look like this. Okay, this variable shows the number 1 when people come from municipality 3. Otherwise, 0. Okay, so if they come from municipality number 1, municipality number 2, okay, then the values are 0. So it's 0, 1 coded. It's binary. It's a dummy variable. Okay? Is it clear? How you generate a set of dummy variables.
Why the table has 7 lines? I mean, maybe this is a particle of the dummy variable shows, but why it is 7?
7?
Yeah.
4, 5. No, I'm just showing the first 7 observations. So actually, there are many. So if the sample size is 246, then you have 246 lines. This is just to explain. Yeah, just showing the first 7 observations. Yeah, it's a good question. So in terms of household ID, yeah, so you have this ID identifier like a variable. Yeah, so all the way to 200 something. Okay. Okay, so this is how you generate dummy variables from a categorical variable, or how you convert a categorical variable into a set of dummy variables. Okay, so now you converted this one into this and this together as a set. Okay, we do not create a dummy for municipality 1 because municipality 1 is a reference category. Okay, same as gender. We only had women dummy or men dummy. We don't have both because it's redundant. Okay, men dummy, women dummy is just the opposite. Right? So no information is carried. Okay, so this one as well. As long as you have municipality 2 dummy and municipality 3 dummy, then automatically from these 2 dummies, you can see who are from municipality 1. Because it's just the rest, just the remainder. Okay? Okay, then how will you include them in the analysis? Okay, so before including, yeah, let's talk a bit about how to generate these dummies. Okay, there are 2 methods. Okay, the second method is actually easier, but yeah, just for understanding, let's talk about this first method as well. First method is just to create the dummies, just like this one. Creating dummy variables, and then include. Okay, so this is just our language to create one dummy variable, this one, which you don't have to memorize because it's in the file. Okay, so in your own analysis, you just need to change the variable name. Okay, so language-wise, you don't have to worry. Okay, but these four lines will do creation of one dummy variable. Okay. Okay, so this first line, this one is to define this variable, but inside it's empty. Yeah, the name can be anything. It's arbitrary. I put it this way because it's municipality. Okay, so moon, and then 2 because we are creating municipality 2 dummy. Okay, and then done for dummy variable. So it's just a name. So we are creating this new variable. Okay. Okay, so in the first line, you put nothing inside, just a name. So empty variable. Okay, by definition, when municipality is 1, you assign the value of 0. Okay? So this line can do it. If you write it this way. So this brackets shows the condition. If municipality, this variable, original variable, if this categorical variable is 1, then you insert this number to this variable. Okay? Okay, the next one. By definition, when municipality category is 2, then you insert 1, okay, to this variable. Municipality 2 dummy. Okay? This one, when municipality is 3, then you assign 0. So you're just doing this one. You're just doing this one based on this. Okay?
Yeah, but sorry. But in case of last line, when municipality is 3, so why don't we use 2? Like
if municipality is 3, we do this one.
0?
Yeah, this one. Municipality is 3 dummy. That means the value is 1 only when the municipality is number 3. Okay?
Not okay. Can you please explain again?
So this one, this set of 4 lines is to create the municipality 3 dummy. Okay? Municipality 3 is defined in such a way that the original categorical variable, if this is 1, then this dummy has 0. Because it's municipality 3 dummy. Okay? If municipality 2, then again it's 0. Only when people are from municipality number 3, you give the value of 1. Okay? Because that is how you want it. This is how we want to define this municipality 3 dummy. If it's a men dummy, then you find the value of 1 only when people are men. You find the value of 0 when people are women. Okay? By the same token, if you are generating municipality 3 dummy, you want the value of 1 only when people are from municipality 3. Otherwise, you want 0. Okay? So that is what is done here. First, you open this variable name. Okay? And then assign the value 0 when the original municipality is 1. Assign the value of 0 when the original municipality is 2. Assign the value of 1 when the original municipality is number 3. Okay? So these 4 lines are just doing what I explained here. Creating this one from the original categorical variable. Make sense? Again, you don't have to memorize this language. Okay? I just want you to follow what is happening. Okay? So it's written here. What this line means, what this line means. But you don't have to be able to write the code. Okay? Okay, so after doing this, okay, so these 4 lines create the dummy for municipality 2. These 4 lines create the dummy for municipality 3. Okay, so after doing all this, now we have this variable and this variable. Okay, ready for analysis. Okay, so those variables, now you include them in the model. So variable name is this one. Municipality 2 dummy and municipality 3 dummy. You just include them on the right-hand side of the equation. Other things are the same. Okay. But of course, I give a different name because it's a categorical variable model. So I just put cat, okay, categorical regression 1 for method 1 because I discussed method 2 after this. Okay, so you don't have to worry so much about this one because this can be any name. Okay, so you include these 2 dummies into the model. Then run the analysis. Okay, so go to R. Maybe we take a break. 10 minutes break, and then come back to R. Okay? Okay. Let's resume. Okay, so to analyze a categorical variable, we created a set of dummy variables. Okay, so let's implement it in R. Okay, so this is what you just observed in PowerPoint. So these 4 lines create one dummy variable representing municipality 2. And the next 4 lines create the other dummy variable representing municipality 3. Okay. So by executing all these, you will have 2 dummy variables created. Okay. For that one original categorical variable, municipality. Okay, this one. So from this one categorical variable having 3 categories, we created these 2 dummies. Okay. Okay, please execute. Choose Control R or Command Enter. Yeah, so just execute it. There's no error message. Hopefully. That means it went well. Okay, everybody got this? Okay, then you have these 2 dummies ready for analysis. Okay, so now you have here 2 dummies included. Mun2 done and Mun3 done. Okay, in addition to what you had before. All right? Okay, then execute this regression. Okay, Control R or Command Enter. Did you get the same result? So now you have municipality 2 dummy and municipality 3 dummy. You got the same? Okay, how is the result? Municipality 2 significant or not? P-value is large. Okay, so municipality 2 dummy is not significant. Municipality 3 dummy, P-value is small. Okay, so this dummy, municipality number 3, is significant. Okay, and the size of the coefficient is like 12,000. Okay, did you get the same result? Then let's see how to present it and also how to interpret it. Okay, so let's start from how to present it. Okay, so based on the result, you put a table like this. So now you have municipality 2 dummy and municipality 3 dummy. Okay. You don't have municipality 1 dummy, right? Because municipality 1 is a reference category. Just like gender. For gender, we have this men dummy. This is actually men dummy because 1 for men, 0 for women. Okay? For gender, we have 2 categories, men and women. But in terms of the number of variables, we use only 1. Okay? Men dummy. We don't include women dummy together. Okay? Because automatically for this, women are the reference category. So we don't have to include. Because automatically this one variable is comparing the 2. Okay? This one, this municipality 2 dummy, this compares between municipality 1 and 2. This municipality 3 dummy, this compares between municipality 1 and 3. Okay? So automatically comparison with the reference category is included. Okay? So that's why we will not have 3 dummies if originally there are 3 categories. Okay? Always -1. Because reference category we don't include. If there are 2 categories like gender, we have 1 dummy. Okay? If there are 3 municipalities, we create 2 dummies. Okay, how do we interpret it? Municipality 2 dummy, this is insignificant. Okay? So the effect of municipality 2 dummy is non-existent. Okay? We don't conclude there is an effect. But municipality 3, there seems to be a positive and significant effect. Okay? Okay, so let's graphically understand it. Again, the x variable is a continuous covariate. For example, education. It can be other variables like land size or age. But because education was significant, we can show this slope. Okay? Because education had a positive effect. So there's a slope for education. Now, just like the case of gender, we understand the effect of dummy variables using these dislocated parallel lines. Okay, so municipality 1 and municipality 3, you found the significant difference captured by municipality 3 dummy, right? And the size was 12474. Okay, so the results shown here, okay, that is represented as the vertical distance between municipality 1 line and municipality 3 line. Okay, the slope is the slope coefficient for education. Okay. Oh. Yeah. So education coefficient, this one is the slope. Okay. This one is the slope. Okay. But the distance between municipality 3 and municipality 1, the vertical distance is the coefficient on municipality 3 dummy. Okay. Now, what about municipality 2? Municipality 2 was negative but insignificant. Okay, so basically you regard them as kind of 0. No effect. Okay, so although it was negative, okay, so negative means if significant, you will have a line here, solid line here. But because it's insignificant, I put it as the dotted line. Okay, so it's not a significant effect. So vertical distance between M1 and M2 is insignificant. So this distance is insignificant. Insignificant means not different from 0. Okay, not different from 0. So you regard them as 0. You regard it as 0. Yeah, just you consider this as same as this line. But for municipality 3, you found a significant effect. Okay. Okay, so in terms of quantitative interpretation, you write like this. Non-agricultural income will increase by 12,474 pesos on average if moving from municipality 1 to municipality 3, holding other factors constant. Okay, so again, you are making apple-to-apple comparison in terms of all other variables. The only difference is which municipality the person is from. Okay, so you don't know the exact reason, but all you know is municipality 3 has tendency of having high income compared to municipality 1. Maybe there are some other factors not captured by education, land size, and age. Maybe some accessibility to jobs. Okay. So unexplained factor. Oh, so a good thing about considering a location effect is it can absorb all the unobservable factors at the district level or municipality level. You don't have to find the exact variables. This can absorb everything. Okay. Okay, another way to interpret. Moving from municipality 1 to municipality 2 will not have any effect on non-agricultural income on average, holding other factors constant. So this one is interpreting this one, the insignificant coefficient. Okay, so that is the quantitative interpretation of the estimated coefficients on dummy variables. Understood how you interpret? So you don't have to draw a graph all the time. Okay, this is just to visualize. Okay, so when you do the research, you just see the table, you just create a table and then provide this kind of statement. You don't present a graph. Okay. Yes. Insignificant one, you can interpret it like this. Okay, as long as you say no effect. Okay, then you can write it. This is also an interpretation.
Non-agricultural income will increase. Only this sentence is okay, or we have to interpret the insignificant as well.
Okay. Yeah, it's okay to go without this one. Because this is the key result. So it depends on how the paper is structured. If you have many other variables to explain, maybe you omit this one. If it's too obvious. But if this is the only result, maybe it's good to mention this as well. Yeah. Okay. Any question about this one. Now the next method is to do this, to do this in an easier way. Easier way, method number 2, you can skip the creation of dummies. Okay, you just tell R, this categorical variable will be analyzed in regression. Then R will automatically show the results for 2 dummies. So you don't have to create 2 dummies and include the 2 in the model. That is also possible. Yeah, so how will you do it? You don't have to memorize it. Okay. But yeah, you use this kind of code. Okay, relevel. This is basically to specify which municipality you want to use as a reference category. Okay, so if you want to use municipality 1 as a reference, then you write it this way. Okay, and then you put this original variable name here. Okay, municipality. Okay, but you have to give this name, new name. So original one is original one. You are not changing this one. Using this one, you have this new variable. It is actually the same as this, but R will recognize it as a categorical variable. So R will take care of it. Okay, so automatically, R will calculate 2 dummies. So you don't have to do like executing 8 lines. Okay, so that process you can skip. Okay, so the only thing required is, to use this one line. Okay, and then you can execute the regression here. Okay, so the variable name, you use the new name, not the original one, but the new one you gave. Okay, so this is one variable, not 2. One variable, but it will be recognized as a categorical variable. So R will do dummy variable creation. Okay, so let's do this. Yeah, let's switch to R. Let's switch to R. It is here. Alternative method. Alternative method. So you have just one line. Just one line instead of these 8. Okay, so it's easier. Okay, and then after this, you execute the analysis. Okay, so now you have this one variable here. Okay, but it will show 2 results, 2 coefficients. Automatically, it will show 2 coefficients. Okay, please execute these 3 lines. Yeah, after executing this one. Yeah, yeah, relevel. Yeah, this one you have to do. Yeah, actually, altogether you can do. Execute. Okay. What do you find? Automatically, it gave two results, two coefficients. Okay. You got the same? Okay. Yeah, because automatically given, the names are slightly different from the last version, but otherwise, everything is the same. Coefficients, p-values, other variables, everything else is the same. Okay, so the interpretation is also the same. Presentation in the table is also the same. Okay, so just a bit of shortcut. Okay, any question about how to analyze a categorical variable as an X variable? You are sleepy?
Professor,
Yes?
so we're comparing municipality 2 and municipality 3 with reference to municipality 1. So does this mean that we cannot compare between municipality 2 and municipality 3?
If you want to explicitly compare municipality 2 and municipality 3, then you can assign municipality 2 or 3 as a reference category.
Okay.
Then you can directly compare.
Okay, so for this, we can only compare between 1 and 2 and 1 and 3.
Yes, yes, yeah. In this current model.
Okay.
Yeah, 1 and 2, and then 1 and 3.
Okay, thank you.
Professor? Yeah, I have a question. As we are including more variables into this into the regression, and some of the variables become not significant. How do we understand this?
Yeah, like age. Okay, so maybe you're talking about the land size?
Yes.
Yeah, this can happen. When you have more variables into the model, basically it's a good thing to consider all the possible factors, okay? And include many variables. That is a very important thing to do. But sometimes X variables are correlated with themselves, okay, with each other. Okay, in that case, the results may change after adding some variables. For example, the result on land holding, previously it was significant, but now the p-value is large, 17%. Okay, so when you consider municipality dummies, then in this model, you cannot find the effect of land size. But instead, you can discuss the municipality effect. Because maybe municipality and the land size are related. Probably municipality 3 has a larger land holding size. Maybe that is the reason. So the land size effect is kind of captured by this municipality 3 dummy as a possibility. Okay. That is probably the reason why field size became insignificant. So yeah, in this kind of case, if both variables are important, okay, if both municipality effect and landholding size, landholding effect are important, then you can run separate models. So one with municipality, another one with landholding size only. That is also what we often do. Okay, so that way you can discuss both municipality effects and landholding effect. Yeah, so this is called multicollinearity. We will discuss it later. So we have a class, and particularly on that one. Okay. Yeah, so in that sense, it's a good question. It's a relevant question. We will discuss it more later. Okay, so now you understood how to analyze a categorical variable on the right-hand side. Okay, now remember, you had one other type of variable, not numerical, not categorical. Okay. Oh. So maybe you finished. Okay. So the next one is we will talk about ordinal variable. Okay. So numerical variable means it can be ratio scale variable or interval scale. Okay. So basically numbers. It can be land holding, it can be age. So that is numerical variable. And then now we considered a categorical variable as well. But remember something in between numerical variable and categorical variable, which is ordinal variable. Okay, so ordinal variable has some ordering, but it's not really a quantity. For example, level of preference. Okay, level of preference for some technology or some practice. Okay, it can be coded from 1 to 5. 5 means strongly preferred. 4 means moderately preferred. 3 can mean neutral. 2 may be not preferred. 1 means strong rejection. Okay. So that kind of different levels can be captured by ordinal variable. Okay. So it's coded like a number 1, 2, 3, 4, 5. Okay. But these are not quantity. So number 4 doesn't mean the double of number 2. It's just a level. Okay. So that is so-called ordinal variable. How do you analyze an ordinal explanatory variable, ordinal variable on the right-hand side as an x variable? Any idea? Question. Okay, so now we discuss how to analyze a categorical variable on the right-hand side as an x variable. And numerical variable, of course, you can analyze. Age, land size, okay, already here, included. Okay, so we discussed how to analyze, how to analyze numerical variable. Like years of schooling, age, field size. Okay, so already it was covered. And also how to analyze a categorical variable, like binary or more than 2 categories. It was already done. So one type of variable which we didn't cover yet is the ordinal variable, like a Likert scale. So that kind of variable, let's say we have one variable representing technology preference. Okay, the values can be 5 levels. Preference level 1, 2, 3, 4, 5. So let's say we have this one variable, which is an ordinal variable. How are we going to analyze it as an x variable. Oh. Oh. Okay. Okay. Yeah, that is a good answer from Gary. Okay, so let's go to the next material. Where is it? Oh, okay, so close this one. This one's done. The next one. Class 13 to 15. Let's close. Oh. Oh. Okay, share the screen. Okay. So what Gary said is correct. We can consider dummy variables from an ordinal variable. Okay, just like we did for a categorical variable. Okay. Again, you cannot include an ordinal variable as an explanatory variable. Okay, just by putting it into a regression model. Although it looks like numbers, 1, 2, 3, 4, 5. Actually, that's the mistake I made when I was in a master program a long time ago. I thought it's okay to do it. Okay, but later found it's not right. Okay. Yeah, so you attempted to do it because it's numbers. Okay, level 1, 2, 3, 4, 5. Yeah, unlike categorical variable, showing some names. Yeah, so that cannot be analyzed. If you put it in the model, then some error will come because the software cannot recognize the text information. But for ordinal variable, because it's coded as numbers, 1, 2, 3, 4, 5, technically the software can analyze. So you may not easily notice the mistake. Okay. You have to, okay, the same way we did for a categorical variable, for ordinal variable also, you have to turn it into dummy variables. Okay, that is very important. That's why I put this red font, important. So class 12 and class 13, very important, because during the course, students remember it, okay, so they can do it. But after some months, when they start doing research thesis, many students forget, okay? And then I send the same slide, this one, again to the student. Then they will remember. Okay, so that's why I put this important thing here. Okay. Yeah, one example. Just as I mentioned, preference for technology adoption. Okay, so 1 can be strongly disagree to use. 2 can be mildly disagree to use. So not 5 levels. Okay, for simplicity, we consider 4 levels. So 3 and 4 basically in agreement to use the technology. But 4 means strongly agree. 3 less. Okay, so different levels of technology adoption, a preference for technology adoption. So maybe in practice, you will give them some training. Okay, you will show some demonstration of a particular technology. Okay, to show them how some technology works. Okay, then after the training, You study their perception. Okay, so now you participated in the training. After the training, what is your preference, level of preference toward adopting this technology? So that kind of assessment you can do. Okay, and then you analyze the result, this response. Okay, you can analyze this kind of response. Yeah, either as dependent variable or explanatory variable. But in this case, we are still talking about right-hand side. Okay, X variables. Okay. Yeah, so generating dummy variables from this ordinal variable, having 4 levels. How many dummies are needed? 3. Because you create 1 less. Okay. There are 4 levels. So 1 level will be taken as a reference category, reference level. Okay. So you will create 3 dummies. In this case, okay. If there are 4 levels, then you create 3 dummies. Yeah, more specifically, usually in the case of ordinal variable, it's easier if you put the lowest level as a base, as a reference category. Okay, and then see how a higher agreement or higher preference will affect the output. Okay, so if you take this lowest level of technology preference as a base category, reference category, then you create a dummy for level 2, and another dummy for level 3, and another dummy for level 4. Okay, are you with me? Similar to what we did for a categorical variable. But the only difference is, because it's ordinal, it has some ordering. 1, 2, 3, 4. Otherwise, it's the same. Okay, then we can do the same thing. We create, in this case, 3 dummies. To create 3 dummies, we do this kind of coding, okay, which is already in the file. You don't need to bother to memorize. Then, of course, you can use method number 2, skipping the creation of dummies. Okay, so instead of writing many lines, you can just do this 1 line. Okay, so you put the original variable, ordinal variable here, take preference, and then you just state the reference category to be level 1. Okay, and then it comes with the new name. New name, you can give any name. Ordinal, okay, ord for ordinary, ord dummies. This is 1 variable. And then you include it in the model as this. Okay, for simplicity, we don't include the municipality dummy. Okay, because there will be too many coefficients. Okay, but in the actual analysis, probably it's better to include. Okay, yeah, but just to keep it succinct, I removed the categorical dummies. Okay, but all other variables are retained. Okay, so you still have education, gender, age, land holding. But in terms of assessing the effect of technology preference, now you have the set of dummy variables. Okay, but in this shortcut method, it looks like just 1 variable. But automatically, I will give you 3 coefficients. Okay, so can you do it in R? It's almost time. Oh. If you are in rush, you can finish. Yeah, because that is the last line. Oh, not last, okay. Okay, so now we have dummy variables from an ordinal variable. This one. Okay, so method number one, straightforward, but you have to do many lines. Okay, this is method number one. Method number two is the shortcut. Instead of, in this case, 15 lines, you can just do it with one line. Okay, so maybe you can just do this one. And then execute. Did you get the result? Like this. Ordinary, not ordinary, sorry, ordinal, dummy, number 2, number 3, number 4. So you have 3 dummy variables and the associated coefficients and p-values. You got the same thing? Okay. Yeah, if you get the same thing, then I go back to the PowerPoint. Okay, so based on the result, you will create this kind of table. So now you have a set of 3 dummies from technology preference. So what can you say about the result? Compared to the lowest preference level. When people have slightly higher, still negative, kind of negative perception, but slightly higher than level 1. Okay? For such people, the coefficient is this, and the p is this. It's insignificant. So no difference between preference level 1 people and preference level 2 people. No difference in the output income. Okay, but for preference 3 and preference 4, these dummies have significant and positive coefficients. Okay. Remember, the reference level is level 1. So this tells you if people's preference level is 3, then compared to level 1 people, preference level 1 people, these people tend to have a higher income. Okay? The amount is higher by this much, 14,000 something. So higher than people who have only level 1 preference. Okay, this one, preference 4. This one also significant, and the coefficient is bigger than preference 3. So that means compared to people who have the least preference for the particular technology, people who have strong preference for the technology have higher income. Okay, And the difference is, on average, this much. So this is the difference between level 1 and level 4. Okay, so all the values are in reference to level 1, which is the base category, reference category. Is it clear? The way we interpret it is similar to the case of a categorical variable. Okay. But in this case, you can see that as the level of preference rises, then the output also increases. Okay, so when people are positive about the technology, then they are likely to have higher output. Okay, that is the implication from this result. Yeah, 2 was not significant, but 3 was higher than 1, and 4 was even higher. Okay. So it's kind of consistent. 3 higher than 1, 4 higher than 4, even higher. Okay, so quantitatively, you can write this way. On average, non-ag income will increase by 14,474 pesos if changing the preference from strongly disagree to mildly agree. Strongly disagree is level 1. Mildly agree is level 3. Okay. Keeping other factors unchanged. You can also interpret this one. On average, non-ag income will increase by 18,000 pesos if changing the preference from strongly disagree to strongly agree, keeping other factors unchanged. Okay, so this kind of interpretation you can give based on this result. Okay, so in this case, it's consistent. As preference level rises, the output also rises. But this kind of result may not be always consistent. Okay, so you may observe preference 3 was higher than 1, but preference 4 may be below 3. So that kind of result sometimes you observe. Then you have a hard time interpreting the result. Okay, so that is also possible. Okay, so in this case, it is consistent. That means the information was captured correctly. Probably the data are accurate, and the analytical method and the model was also correct. Okay. Okay, any question about analyzing an ordinal variable? Green words. Yeah. So carefully consider the interpretation of this kind of result, where the effects do not monotonically increase, decrease with levels. So you have to be careful with preference 2. For preference 2, the difference from preference 1 was not significant. Yeah, so it's not always increasing. If it's always increasing, we say monotonically increasing. If it's always decreasing, then we say monotonically decreasing. So it's kind of monotonically increasing, but except preference level 2. Yeah, otherwise, the increase is monotonic. Okay, 3 is higher than 1, 4 is even higher. So if the result is not monotonic, either increasing or decreasing, if it's not monotonic, then interpretation will be tough. Okay, because you need to justify For example, preference 3 had the highest output. If preference 3 had the highest output, then it will be a bit difficult to explain. Okay, you need to justify, mildly agree. You need to somehow make an argument that this is better than strongly agree. Okay, so if the result will be like that, then sometimes the interpretation can be difficult. Okay, but if the result is like this, just like this, then it's relatively straightforward to explain. Okay, does it make sense? If no more question, we finish. And then see you tomorrow at 4 p.m. Okay, see you tomorrow.
Thank you, sir.
Thank you, Professor.